Exotic forms of matter. The universe is not all that we see, rather it's what we're used to. But like dark matter, there seems to be more to it than that. But even within the realm of normal matter, electrons, our day-to-day particles that power our devices, there are states they can be coaxed into that make them unfamiliar, something else differing a bit from the familiar. In 1934, Eugene Wigner hypothesized that under the right circumstances, very controlled circumstances that require a form of perfection, electrons could form themselves into a kind of lattice, a frozen crystal, if you will, made only of ghostly electrons. In this case, electrons sandwiched between a perfect, it literally has to be perfect, medium to form up into a two-dimensional crystal at extremely low temperatures. But the Wigner crystal was elusive. Attempts to create one before now yielded ambiguous results and questions as to whether one had indeed been created. My guest today did it using perfect graphene, sandwiching electrons, and not only that, he and his team imaged it with a scanning tunneling microscope and have given us our first views of the fabled Wigner crystal.
You have fallen into Event Horizon with John Michael Godier. All of us at Event Horizon love and play video games, but I am the resident Star Trek expert. So let's bring shields to full and power the phasers as I tell you about Star Trek Fleet Command. Set in the ever-expanding Star Trek universe, you can recruit legendary characters and crew iconic ships, sending them on missions of exploration as you expand your territory in this 4X MMO game. I love being able to engage players around the world in battles using resources to upgrade my fleet of starships. There truly is a thriving community of real players to support your journey through the Star Trek universe. Also, be sure to get the Gorn Eviscerator, which is able to open wormholes for quick movement between systems, enabling players to bring their Alliance members to their current location instantly. Star Trek Fleet Command is available on desktop and mobile with a Scopely account. You can play at home or on the go seamlessly. Join us and become members of a mighty alliance by installing Star Trek Fleet Command and immerse yourself in the Star Trek universe and click the link below to become the greatest commander in the universe. You have the con, Commander. Today's fascinating interview is with Professor Ali Yazdani. Professor Ali Yazdani is the James S. McDonnell Distinguished University Professor of Physics at Princeton University, the co-director of Princeton Quantum Initiative, and director of the Princeton Center for Complex Materials, an NSF-funded Center for Materials Research in Science and Engineering. He is known for his research in advancing our understanding of emergent quantum phenomena by application and development of high-resolution microscopy techniques to directly visualize highly entangled quantum states of matter.
Professor Ali Yazdani, welcome to the program.
Thank you for having me.
Doctor, there has been a mystery since the 1930s, ever since Eugene Wigner envisioned and hypothesized this very strange form of matter, the Wigner crystal. Could you give us a rundown on what a Wigner crystal is?
Sure. So in the 30s, right after the discovery of quantum mechanics, physicists started applying quantum mechanics to all kinds of things. And understanding solids became one of the main important part of extension of quantum mechanics. So in the 30s, basically, it was realized that electrons moving in a periodic potential, which we have in a crystal with atoms, how that changes the electronic behavior from that of electrons moving in vacuum. So the notion of what we call electronic bands was first developed. And this is how you can understand the difference between a metal and an insulator and a semiconductor. Now, one of the questions that was sort of immediately realized is, okay, electrons repel one another, they're charged objects. So how do we fold this into this theory? Because the theory that had been worked out is what we call a single particle theory. You basically imagine that the electrons are moving independent of one another inside a crystal, And you for the most part, you ignore their interactions. Now you might say, well, how is that possible? How would that possibly work? And this actually remained somewhat of a mystery till the 1960s. But the basic notion is that you can think of electrons moving in an energy band where they can have a bunch of different energies. They have a lot of room to kind of, if you wish, they can be at many different energy levels in which they could reside. And as a result, the initial understanding was that the interaction between the electrons would be a small correction. Now, this is sort of how you first think about this. And Wigner basically started thinking, when does this correction become non-trivial? And the basic notion comes about in Wigner's paper is that he tries to compute what the electrons would behave, how they would behave if their density was very, very low, meaning that there were very few of them basically moving around a crystal. And he envisioned this problem for trying to understand low density metals. So he basically analyzed this problem, and he realized that there could be a situation under which the repulsion between the electrons can far exceed their kinetic energy. And the kinetic energy is what we think about when we think about the energy of a band. Being able to be at different energies and momenta essentially gives you the feeling that your kinetic energy is kind of a large quantity comparable to the interaction between the electrons. And he calculated that electrons could potentially crystallize. And this could happen at very low densities where the repulsion overcomes their kinetic energy. And the lowest energy state for the electrons is no longer one in which they're moving around the lattice, but in which they're localized in space. So this is where the idea initiated. Now, this sort of notion was something that people tried to see whether they could realize in different experimental situations. And it wasn't until the 1970s where researchers at the old Bell Laboratories in New Jersey realized that they could create a very clean electronic system in which electrons can repel one another in a very controlled situation. What they did is they took a surface of liquid helium, which is when it's cold, and they sprayed with electrons. And these electrons kind of bound to the surface of helium and they don't enter the bulk of the liquid. So you just have like a sheet of electrons floating around on the surface of liquid helium at very cold temperatures. And in this situation, you can have the electrons basically feel each other's repulsion. And, there's no atomic lattice to speak of. You have a liquid kind of underneath, and which could be quite quiet if you make it superfluid, for example. And what they did was they sort of used a way of measuring resonant absorption of electromagnetic field to realize that when they made these electrons at the right densities where you could imagine crystallization to form, they were behaving like as a rigid body in which you could absorb and emit radiation like a resonant object, like a stiff object. Kind of like, you hit a piece of, metal, something that's rigid and it rings. You can kind of think of it like that. So they reported on this, and this was the first instant of what I would say a kind of an indirect way of knowing that there is a Wigner crystal there. Now, of course, you talk about electrons being localized in space. You can also think about, well, what about their quantum mechanical behavior? After all, electrons are also waves. And then you can think about this Wigner crystal being in different regime, what we call in a classical regime, where the distances between the electrons is so large compared to what we call the de Broglie wavelength, which characterizes their waviness of the electrons. Or you can be in the quantum regime, where the distance between the electrons can be comparable to their de Broglie wavelength. So the experiments I just described at Bell Laboratories were done in the classical regime. So on this discovery, people also thought about whether there were situations on which you could have electrons be crystallized in a Wigner crystal inside like a material, like Wigner had originally thought of, a low-density electron material. Now, with the advent of semiconductor heterostructures, where you can basically grow one type of semiconductor on top of another, people realized such low-density electron situation. Theoretically, also people realized that if you apply a large magnetic field, magnetic field makes electrons go in a circle. So this, you can kind of almost think that if you had a large enough field, they would already kind of be localized, right? But not completely. So there's other physics that happens when you have a magnetic field. We can discuss that later. But they realized that if you apply a field, you can actually make the crystallization of electrons appear in a larger range of density, as make it experimentally more easy to access. Now, why is the density important? Remember, you cannot make everything perfect, in terms of, okay, liquid helium can be almost perfect, but you couldn't pack electrons close enough on the surface of helium to get into this quantum regime. But materials are never perfect. So if you make a crystal, if you make the electrons dilute, is a dilute gas or liquid, if you want to think of it that way. If you have any imperfection in the material, then they will play a role by just trapping the electron. So to make a long story short, there's been kind of like 30 years of research in these two-dimensional electron gases in semiconductors, where there have been many different types of experiments, including that resonant experiment that I described to you on the surface of helium, where people have found some signatures that they have identified as the Wigner crystal forming. So what are these signatures? The signatures are like, well, if you have a crystal, it's stuck. So if it's stuck, if you try to flow it, it would be hard. So if you try to pass a current, the electrical current, the Wigner crystal won't move until you maybe slide it. So if you found sort of a non-linearity in how a current flows as you apply a voltage, theories could sort of say, well, maybe this is a signature of the Wigner crystal. Or the same kind of resonance experiment I described earlier on the surface of helium. So this is sort of the status of the field and the methods in which people have used to try to see whether the Wigner crystal is there till our experiment came along. Now you might say, what's the problem? Why would you want to do more experiments? Well, clearly, if you have an indirect method, there could be other interpretations. So for example, as I described, the importance of imperfection in the material, it could be that you have a Wigner crystal, but it's not really a Wigner crystal. It's just electrons stuck to defects. They don't move. You think it's a crystal, but you just depin a kind of a disordered lattice. And the thing in the physics term, what's really interesting about a Wigner crystal is this idea that repulsion between the electrons suddenly spontaneously breaks the symmetry of the continuous symmetry of space, and electrons organize into hexagonal lattice. This is what Wigner predicted. And its density would be tunable continuously with how many electrons you have. So this is where we come in. We do imaging of interesting electronic states in materials. So this was on our target list for a long time. So maybe I should pause there and see if you have any questions, and then I can keep talking.
We're going to go into graphene territory and how you can trap all of this and get it in a position where you can image it. So what is the role of graphene here? And again, about perfect surfaces. How do you make perfect graphene for this?
Very good. So as you know, as your audience probably knows, graphene was isolated, is a shingle sheet of carbon atoms, which was isolated, in the early 2000s, a Nobel Prize in 2009. And it's just basically carbon bonds in a sheet. And, carbon bond is a very strong bond, and it's very hard to break it, just from diamond. So therefore, once it's made, it's very hard to make it imperfect. So this already tells you what graphene is a kind of a magical material, is because if you isolate it, first of all, is this atomically thin thing that we can actually pick up and put down remarkably because it's very strong. It's flexible, which allows us to sort of stack it. And as I'll describe, that's a key part of this experiment. And because of the carbon bond being very strong, it's very hard to find imperfections in it. Now, even though the graphene itself is maybe quite perfect, what do I mean by that? I mean, imagine you have, say, 5 micrometer by 5 micrometer of a sheet of graphene, single atomic layer, and you'll be hard pressed to find a missing atom in it. That's what I mean by perfect. Even if it's perfect, when you handle this thing to try to create a sample in which you can put it in a kind of capacitor to load or unload electrons into the sheet of graphene or make electrical contact to it, there could be other material around that could deposit on the surface of this sheet of graphene and make it dirty. In fact, we didn't come to this field of studying graphene with our instruments early. We are actually kind of latecomers to this game. This has been studied since the discovery of graphene. But what we brought to the table through a story which is kind of unrelated to Wigner was we developed methods in which we could make the graphene, when we pick up and stack graphene structure. So the structure of our experiments is you use a graphite backgate. Graphite is just basically a very thick layer of many sheets of graphene. And then we use a material called boron nitride, which is a dielectric. And we stack on top of it this, in our case, in this case of this experiment, it's 2 layers of graphene. But that's not so critical for the detail. It's a detail. And we put that all together. And the way you do this is you use basically using glue and you just polymeric materials to pick up and put down these layers. This is another really fascinating thing, because you can use the sort of the melting properties of this glue to make them sticky and make them runny, to basically stack these layered materials on top of one another. Now, of course, when you're using glue, there will be residue. What that is just foreign atoms sitting on the surface of graphene. So, we do a lot of experiments that are sensitive to surfaces. We use the scanning tunneling microscope in our laboratory to basically image electronic wave functions and where the atoms are as well, under ultra high vacuum conditions, at low temperatures, and in this case, also in high magnetic field. So if you have any kind of dirt on the surface, we would see it. And through the last 5 years, our group developed ways in which we could make kind of like, almost like half a micron area, maybe sometimes a little larger, essentially of perfect graphene, like no adsorbates on the surface. The only disorder comes from, I mentioned we put this in a capacitor-like device, where the other electrode in this case, so one electrode of the capacitor is the graphene, and the other electrode is this graphite, what we call backgate, which we use to sort of charge up the graphene layer on top. And the only imperfection in our device is sort of the imperfection of the surface of the graphite underneath, which we haven't worked to perfect further at this time because we haven't needed it. So this became our sample. Now, why were we looking at the sample? Well, the Wigner crystal was on our radar because colleagues which measure transport properties, electrical transport properties through these 2-dimensional materials like graphene, had seen these signatures of Wigner crystal, like nonlinearity, IV, and so on. So we kind of knew it had to be there, but we didn't think we could actually image it. And the reason is that the way our imaging technique works is as follows. The scanning tunneling microscope operates by bringing a sharp metallic tip close to the surface of the sample, such that the electrons quantum mechanically can tunnel between the tip and the sample. So when they tunnel between the tip and the sample, you get a small little electrical current that you can actually measure. And what you do is you use this current in a feedback circuit to basically raster the tip across the surface, for example, at a constant height above the surface. This is how an STM works. But what I just described to you is that there is a metallic tip, and also there is a tunneling electron involved in this imaging process. If you told to an average physicist, I was going to use this to image a Wigner crystal, they will point out immediately 2 problems. First, they would say, you got an electrical current. How could this not disturb the crystal? The current is very small, but that was also not clear to us that it would work, even though it's small. Now we are understanding why it's working, which we can get into it. But the other thing is there's a metallic tip. Metallic tips, are like an electrode which can interact, like electrostatically interact with the sample. And an average physicist will say, well, this will perturb your Wigner crystal. But, through the years, we've discovered that in order to make non-invasive measurements of these graphene systems, we have to prepare our tips in certain ways in order to avoid these problems of sort of modifying what we are measuring from the microscope tip itself. So we were overcoming those problems for other reasons. And once we were in this situation where we were studying this experiment, the students come to me and they say, I think we're seeing the Wigner crystal. So they had the graphene this is at around 200 millikelvin or lower, and it's in a high magnetic field around 14 Tesla. And we were studying this for a number of different reasons that we can get into. There are other phases electrons can make that are very exotic, as well as the Wigner crystal. And then they started imaging this, and under certain conditions, we discovered that we can unperturbedly see the periodic crystal that is made out of electrons. And in this device, what you could do is you can change the density of electrons by tuning this capacitor. And just right there under your nose in the microscope, you can change the lattice constant continuously, and you can watch it under the microscope in the scanning tunneling microscope. And it turns out there are no fitting parameters because we know the charge of an electron, and then that will sort of immediately tells you what the lattice constant you should be measuring. So everything that's sort of predicted from theory can be directly compared to the experiment, and there are no sort of adjustable parameters. You just have to make sure your microscope is well calibrated so you don't make a systematic error. So this is kind of the story of how we got to the point of actually visualizing this Wigner crystal.
Now, in regards to this crystal, this does not strike me as something that's going to happen in nature on its own. Am I wrong? Could this happen in an environment like, I don't know, a neutron star or somewhere? Or is this potentially the first time anyone in the universe has ever created a Wigner crystal?
That's a deep question. I have to think. I mean, I would say, there might be there are no situations that we know of. I mean, so that's why we wrote this paper, where anybody has seen one where you can definitively say you've got a Wigner crystal. Okay, so I guess your question, I take it to mean, could it happen in other circumstances? So, I mean, going back to Wigner's original idea, it could happen if you made some material pure enough and with low enough electron density. It could happen. It hasn't happened, but it's possible.
Now, this also strikes me when we're messing around with moving electrons around and arranging them, essentially, or making them arrange themselves. It sounds like something that in the far future could have a practical use. Can you imagine a use for a Wigner crystal as we get better at making them?
Well, I would say, so let me say a few things about what are other phases that are near. So Wigner crystal, I think that the thing to kind of appreciate a little bit about the Wigner crystal is that it's probably the oldest phase of matter in which essentially interaction between electrons dominate the physics. And since then, we have found other phases of matter, which that comes to be. So actually, in our experiment, and one of the reasons we did this experiment is that just as you change the density of electrons in this 2D system, when you have the presence of a magnetic field, electrons can also form these other phases known as the fractional quantum Hall states, which come about of the interaction between the electrons themselves. They make a very complex liquid, actually, that has actually properties that are very similar to a Wigner crystal. It can be, but it has some other special properties that are different than a localized crystal. So insofar as saying, what is this good for? I would say that trying to understand interacting phases of electrons can have many applications, and I can get to the applications in a moment. And what this Wigner crystal is probably the most is one of the fundamental ones. It's one of the simpler ones. And now we have a method of really studying in ways that we couldn't study before. For example, one of the things we discovered in our experiment is, so we talk about this being a crystal, right? And we talk about the electrons living somewhere. And remember at the beginning, I talk about this de Broglie wavelength. So now you can ask the question, what's the shape of a site of an electron that lives in it relative to the distance between the two electrons? So it turns out in the crystal that we image, if you think about the root mean square motion of the electron, or how, what distance does an electron occupy in the lattice versus the distance between the electrons, that ratio is just like 1/3, which is completely amazing because it tells you that if electrons in this crystal are actually quantum mechanically tunneling between the different sites where they are sitting. So there are processes where electrons are getting exchanged in this crystal, which we know must be happening because of just the look of our picture. So insofar as trying to understand interacting electrons, this provides a really powerful platform to study them in detail in one very interesting setting. Now, in terms of application of interacting electrons, you can think of several different applications. One of them is that these electrons that form the Wigner crystal, when they melt, they can melt into these states that are called the fractional quantum Hall states. And these fractional quantum Hall states are truly bizarre because in them, electrons are no longer, they're so interacting that they make this interacting soup where when you think about what's sort of the basic excitation of the system, you don't think of an electron anymore. It turns out you actually think about things that are like a fraction of an electron, okay, in charge and in behavior. And these fractionalized electrons, that's how we call them, may have application in which we can write quantum information into their properties. So this is actually something that relates to quantum computing, these other phases near a Wigner crystal. So we are on this exploratory path now, having imaged electrons being localized. Our next aim is to try to see whether we can directly visualize these fractionalized particles that have potentially, quantum information applications. So I don't know whether that gives you a flavor for, where this research can go, but electronics is one in which we are very used to thinking about electrons and properties of an electron, but interacting electronic system can do electronics in ways that could be completely different. And this is sort of one of the frontier areas in physics, is to use those properties to create other kind of electronic sort of devices and qubits and whatnot. So, the path of studying interacting electrons, as we are doing in this experiment, is sort of along that road.
Now, Doctor, with a quantum tunneling microscope, and this is truly amazing if you think about that. This is a quantum mechanical microscope that you're using to study this. Mm-hmm. Walk us through exactly how it does it, but also, again, we're in the quantum world. Does the fact that you're measuring it change the equation?
Yes. Very good, very good. How does it do it? So quantum tunneling is the process by which, if you have a barrier which is thin enough, then while in the classical world, a particle which has an energy below that barrier cannot go through, in the quantum world, the particle penetrates that barrier some of the time. And if you probabilistically watch it, at some point it will get to the other side, which is truly an amazing thing to think about. And every time I teach it, I'm still amazed by it, even though I use it every day to make a living. Now, the microscope, which was invented in the 1980s at IBM, was basically intended, it was a device actually motivated by a technological problem. IBM had a problem in actually making superconducting circuits, and they wanted a microscope that could image the surface electronically. And Binning and Roll basically building on work of others and their amazing innovations, they basically realized that if you can stabilize, vibrationally stabilize a tip a few angstrom, few atomic thicknesses away from the surface, and you could certainly measure the current. This was actually done before them, but then they realized that they could use feedback electronics, use piezoelectric elements to actually controllably move this tip and turn it into a microscope. So that was the birth of the scanning tunneling microscope. But actually, what I use it for is not so much as looking at atoms, is looking at electrons. Well, of course, everything they measure and we're measuring is looking at electrons because it works on principle of electron tunneling current. But we use it in a way where there are different modalities of this microscope where you could measure the rate at which electrons tunnel. And this rate of electron tunneling can tell you very important information about the probability of electrons being there some places. And you can map this probability not just in the spatial domain, but you can also map it in the energy domain by varying the voltage between the tip and the sample. So this microscope, these pictures that you see from our group is basically, we've done this for 20 years, where we turn this instrumentation into a true, I think, quantum microscope, because we're looking at electronic waves, or in this case, electronic crystal. Okay. So, and there are certain things that goes into optimizing those measurements that we have developed over the years, advancing beyond just looking at atoms, which is what it was invented to do. Now, insofar as being perturbative, that's for sure. You are perturbing the system. But there are different levels at which you're perturbing it. There is perturbing a system insofar as really changing the ground state of the system. We are actually measuring excitation properties. So those things can get perturbed by the microscope, but you're basically you're asking the system, what's your first excited state look like? So that's a little different than ground state properties, in which you're putting something in a quantum superposition, and this is stable, and then you measure it. So we have a system which is in some quantum state, but the kind of questions we are asking, the way we are measuring it is we are basically exciting it and saying, how do you want to respond to this excitation? And that's a way in which our measurement is changing the system, if you will. We are just exciting it and asking, what's your excitation like? And just for the system giving us that answer, although we are changing it, we find a lot of information about it. And insofar as this crystal goes, it's telling us its excitation we know actually exactly there is a threshold, for example, to being able to actually see the crystal. If you're below a certain threshold of probing, you cannot see the crystal at all. And we can sort of see if you increase the threshold in which you sense the system, everything becomes a blur and we cannot see the crystal anymore. So we can modify it, that's for sure. So insofar as creating an excited state that's a way in which we are making a measurement of the system. That's for sure. We're not looking at a ground state.
Now we're talking about low temperatures and very special conditions. But when you begin to return to normal, the crystal melts. Could you explain that? And what happens? I mean, is there strangeness there?
Well, so a two-dimensional crystal of anything, atoms, electrons, actually melts in a way that is very unusual. In fact, it's so unusual they gave it a Nobel Prize for it a couple of years ago. Costas and Thales shared the Nobel Prize with my colleague here, Haldane, on basically describing the mechanism of melting a two-dimensional crystal. So that in of itself is so the way it melts in the thermal sense, when you raise the temperature, it actually you make defects, and these defects proliferate, and it has a whole melting mechanism. But the more interesting part is what we call quantum melting. What does that mean? So you're very familiar with the idea that you have your ice, you add temperature, you think about atoms being in a crystal, you get more thermal motion, at some point you break the bond, and voila, you have a liquid. Imagine you're at zero temperature, but you have some other parameter. In our case, just the distance between the electrons. There's something called quantum fluctuations, which is coming from quantum zero-point motion, the things that we know are always there because of quantum mechanics, Heisenberg-Yazdani principle, telling us about, ideas about, what's the minimum sort of vibration you can have in a quantum system. That's what drives the melting of this lattice. And that's something that we are studying now. And that's also very cool. In fact, we already reported in this paper some rather strange findings, which is the crystal melts. So what does that mean? So when I say a crystal melts, if you think on average, there is a distance between the atoms, right? So that's the lattice constant. But there is also orientation between the atoms, if I was talking about an atom crystal. But also here, I'm thinking about an electron crystal. They're in a hexagonal lattice. They have a certain lattice constant. So there is a symmetry to that lattice, right? But now what happens if you change the density of electrons in this Wigner crystal? What happens is it melts. It makes a structure. If I showed you the picture in the face of a crystal, you would clearly see objects that you would call, oh, that looks like an electron. And when it's melted, you see some patterns. It looks like a standing wave sort of pattern. It has some length scale to it. has some a characteristic modulation in space. But then it kind of looks like a wave. And if you were to ask, where are my objects? You wouldn't be able to point them out anymore. You know what I mean? It just looks like a pond that you're throwing, rocks in. It's just ripples on a pond. But what's curious about this liquid-like object is the distance between the crest and the trough of between the crest and the crest of the waves that we see is like the distance between the electrons in the Wigner crystal. It's very close to that number. So we are finding very strange ways that it is melting, because of this quantumness. And we are trying to understand that. And there are some theories that sort of pertains to this observation, which might be related to what we have seen. But yeah, it is. And when it melts, it could also melt into these very exotic quantum liquids that have very strange, fractionalized particles. So that's it. So melting with temperature is interesting, but this is more interesting as you change ground state with quantum mechanics and think about quantum melting.
In regards to the Wigner crystal, so in the past we've had some groups saying, well, we created one, we think, and there was ambiguity about it. But this one didn't do that. This one behaved exactly as predicted and formed up in sort of triangular structures, and everything that was predicted, this very compellingly was a Wigner crystal, right? Mm-hmm. And why does it do that? Why does it form the triangles?
Well, it's like it's like this is the simplest closed pack structure you can have, right? You look at the honeybee's hive, and you'll say, why does it look like that? It's because round-headed objects are trying to stick their heads together, and basically this pattern emerge. Okay, so this is a story of emergence, right? The story of emergence is that certain symmetries arise out of basically some basics of interaction. So the crystalline symmetry here emerges from the fact because of the symmetry of the problem. Okay, and it's the lowest energy. Now, I should say, we did find some condition where you can make some other kind of crystal, which maybe. Well, I don't expect you to read the technicality of all these papers, but one thing we did report in this paper was when we lower the magnetic field, which lowers the interaction between the electrons, we make another phase that people had predicted. It's called the stripe phase. So what's a stripe phase? So a crystal is one where you got electrons, they're sitting there, in a hexagonal lattice like we described, triangle lattice. A stripe phase is one in which they're crystallized in one direction, and in the other direction in space, they're not crystallized. So just by the name suggests, it forms a stripe pattern. So we did find that when we reduce the interaction between the electrons by lowering the magnetic field, which is the knob that we have in the lab to do that, it makes a phase transition to this stripe phase. And there are some theories that predict that in the particular situation in our experiment, given that we're using graphene and how the electrons behave in a magnetic field, in this bilayer graphene, that would make that a favorable state. So the hexagonal pattern, the triangular lattice, is one that is most natural it's the most symmetric structure you could make. But there could be a situation where you will make other things, and we found one, which is the stripe phase. And there could be situations we could make other kinds of Wigner crystal, which are not triangle. They could be square. If you put other interaction in the problem between the electrons, it turns out that other phases are possible.
How stable is it? In other words, you create this two-dimensional Wigner crystal between a sandwich of graphene. How big can you make that? And in other words, is this just something you can only do at very small scales, or could you make one, I don't know, the size of a cell phone?
No. I think it would be at most, it's just limited by the, how clean you can make the graphene. That's what it looks like. And its environment. So right now we have achieved maybe a micron is sort of our limit. And since we are microscopists, we are not so motivated to try to make it bigger. We just have to make it big enough, right? So that we can find the sample and so on. But there are some advantages to make these situations such that the crystal can be formed over a bigger area. Because, for example, you could try to study these melting transitions more carefully, and you need a kind of a larger field of view to get a statistically sort of significant information. But right now it's limited. Basically, the graphene flakes themselves in our lab are no bigger than 20, 30 microns. But there are people who are making large sheets of graphene, and for electronics application. I don't know how clean some of these things are and how clean devices you can make. But right now we are just working within a few microns in our lab in terms of clean areas of like 20 micron device.
What was your reaction and your team's reaction when that image appeared? In other words, when I looked at it, I thought it has a certain beauty with the triangles. It's beautiful. What was your guys' reaction when that image came out and you saw it?
Well, I wasn't there. It was in the middle of the night, as usual. So, Yen-Chen, my graduate student, we had talked about, well, let's look for it. It should be there. So, we thought about it. And a couple of funny stories I could tell you about it. One is that, they found it. They found it and they told me the next morning. And I came in and I said, well, if it's, this happens in my lab where people think they found something really exciting. And I said, that's great. That's great. Okay, now here's your list of things to do to make sure it's right. And of course, that could take a long time. And it did take a long time. It took 6 months. So my reaction was, wow, we really got a microscope which can really see a single electron stuck there. This is kind of, you pinch yourself when you see things that people tell you, oh, you'll never see, because your experiment won't be able to do it. So that was very cool. But what was funny was that, as the data came in and better and better and better, and they were comparing it to theory, one day in my office, they bring the curves and the curves are like systematically offset from one another, the theory versus experiment. They start sort of thinking, oh, maybe there is some, and it was pretty funny. I said, I'm going to bet money that this is just a slight miscalibration of your microscope. And they hadn't calibrated the microscope under specific conditions where they did this measurement. So they went back and they recalibrated the microscope, and it was like dead on. That's when I was amazed. When I said, oh, there's this like systematic offset. Is that real? Or is that just like a bad measurement or bad calibration? Shit, that's what I thought. That this is really cool, right? This is why physics is, amazing, right? You put the numbers on a piece of paper, and you go do an experiment. And it's all complicated machinery. 100,000 things could go wrong. And then when it all goes right, you sort of see something, and you're like, well, I must have done everything right. And is this offset? And then you might want to be want to go back and change your equations. And you're like, no, nature doesn't lie. So maybe I made a mistake. So those I love those, because it's like you got to stick to your story to make sure you did everything right.
Well, that's the scientific method. There's a reason we do that.
There's a reason we do that. Well, the thing is, as trained as people are, excitement kind of gets in the way for you. So that's why you have to have team members go check their work.
Well, biases, you have to examine everything to make sure and try and knock it out.
That's right.
Just do everything you can to knock it out before if it's still standing.
Absolutely. Yeah. And, and the review process was very interesting as well, because the reviewers weren't like, this isn't right. They were like, well, how is it possible that you're not modifying the crystal? So they made us do lots of check experiments, like change the conditions under which we were measuring things, just to see when we do modify it, when we don't modify it. And I think this was also very helpful, because we could see that, there's a sweet spot where things work. We just got lucky. We hit the sweet spot, but then you could have also missed it.
Now tell us about, so this is actually a probe into the quantum world, actually looking at a subatomic particle, an electron. And again, it's weird.
Well, we're looking at electron waves moving in a crystal. We're not looking at a single electron. Yes. Right.
So tell me about blurring. How weird is it compared to looking at a macroscopic object?
Well, I mean, the thing is that, everything is, so when we deal with most experiments, we're looking at the wave nature of the electrons. And also in this crystal, when I talk about this sort of average site of where the electron is, when we talk about blurring, that blurring is a real thing, is a quantum blur. And the way to think about it is like this, is you have a crystal, and this crystal has a vibrational modes, right? Just like any crystal does. It can jiggle. The atoms jiggle here, the electrons jiggle. But here they do the quantum 0-point motion. And that's what's giving us so when you look at that picture, those little round objects you see, that's the quantum blurriness imaged directly. In fact, that's what we're imaging most of the time.
Now, my last question for you today is the other states that electrons can produce, other than the Wigner crystal. Tell us about some of those, and what's next for your research? Are you going to go and try to do other states?
Oh yes, this is what we do. This is what my lab does. There are a lot of people know us as, any exotic state you can think of. We'll just go try to image it and manipulate and then look at it in this way that is kind of unique. And there are a few people in the world who do the same thing. But this is kind of our core competency, if you will. Now, so I mentioned these nearby states where there are these fractional quantum Hall states. And I mentioned these fractionalized particles, which are like electrons that are fallen apart into objects with fractional charge. And we have a lot of evidence. The Nobel Prize has been given for these discovery of these states and explanations of these states. But actually manipulating these exotic quasi-particles, as we call them, we don't call them electrons. We don't talk. We call them quasi-particles, because they're kind of particles that emerge as excitations of a quantum system. But they could behave like individual particles, meaning what? They could sit somewhere, they could be trapped, they have a charge, and you can move them around. And so this is kind of where we are kind of headed, is trying to see whether we can actually see these fractional particles. People have sensed them locally using some techniques, but there's not been individual quasi-particles. They could actually make their own Wigner crystal. That's another prediction. If you find a low density, sort of create a low density condition of these fractionalized electrons, they'll make a crystal that has a different lattice constant that is determined by the charge of the fractional charge. It's completely bonkers. If this actually is there, we can actually see it. So that's pretty exciting. And I think going in the direction of connecting these fractionalized excitation to try to encode quantum information into them is another thing that I'm excited about. And these experiments sort of getting us closer and closer to really image and sort of get the simpler states and now maybe more complex states nearby. And this is actually it's in the same material. It's not even this different sample. It's just the conditions have to be improved. The samples may have to be made more perfect. Measurement condition, we might have to devise different measurement ways to not perturb them. We just have to figure it out. So these are the future directions in the field. And I should also say there are situations where Wigner crystals can form in some new materials, which are also two-dimensional, not in the presence of a large magnetic field, and not maybe at very low temperatures, maybe like 10 Kelvin or something. And those materials could also be really interesting to study because, they could have their own exotic properties that is different than the Wigner crystal we have here in a magnetic field. So that's also another direction that we are headed towards.
So this brings up one last question. All right, let's flip it around. The positron. So could the anti-scientist in the antimatter world create an anti-Wigner crystal and look at it with his anti-quantum tunneling microscope?
Oh, we are on our way there already. Because in a solid, so when we talk about electrons in a metal or a semiconductor, the antiparticle to an electron, you're thinking about positron in the vacuum, it's what's called a hole. It's not a very exciting name, but it's just the same thing as a positron. Remember, electron and positron come together, they annihilate, there'll be a flash of light. Remember that? The same thing happens. You know what that's called? An LED. An electron and a hole combine and give out light. You use it every day. You're probably looking at the one right now. Okay? And those holes can also crystallize.
It does. That's absolutely amazing.
Does that make sense?
Yeah.
And I think
almost there. I look forward to interviewing again when you get there, because I hope we can do this again sometimes, because this was absolutely fascinating, and I don't think we even touched 1/10 of what was there.
Well, thank you so much. Your questions were great.
I was fascinated the whole time. Captivated.